Good morning, everyone. My name is Wardi Kaharudin from School of Electrical and Electronic Engineering, University Science, Malaysia. Today, I will present our study titled Comparative Evaluation of YOLOv11 and RT-DETR for surface defect detection in metal manufacturing with data augmentation. Here is the outline of my presentation. First, I will explain the motivation behind this research. Then I will share our contributions, followed by our methodology, results, and finally the conclusion and future work. Let's start with why this research matters. In steel manufacturing, surface defects can affect product quality and operational safety. Traditional inspection methods like manual checking are slow, subjective, and not reliable when lighting or surface texture changes. Nowadays, deep learning is widely used to solve this problem. There are two main approaches: CNN-based models like YOLO and transformer-based models like RT-DETR. In this study, we compare these two deep learning architectures for metal surface defect detection. Our study has three main contributions. First, we compare YOLOv11M and RT-DETR under the same training conditions. Second, we analyze how each model performs on difficult defect types. Third, we provide practical guidance on which model architecture is better suited for real industrial inspection. For our dataset, we use a NewDet dataset, which is a well-known benchmark for steel surface defects. It has 6 defect categories. We use 1,440 images for training and 360 images for validation. We compared two models. YOLOv11M is CNN based. It uses local convolution filters and has 20 million parameters, requiring 68 gigaflops compute power. RT-DETR is transformer based. It uses global self-attention, which means it looks at the whole image at once. It is bigger with 1.9 million parameters and need 103.5 gigaflops compute power. To make the models more robust, we apply data augmentation. This means changing the image slightly during training. For example, adjusting brightness and color, rotating, moving, or scaling the image. Instead of choosing these values manually, we use Ultralytics automatic tuning tool to find the best settings. This augmentation helps simulate real factory conditions like different lighting or camera vibrations. For evaluation, we use standard metrics, precision, recall, F1 score, and MAP. Each model was trained for 100 epochs, which was enough for the models to converge. We use an NVIDIA RTX 5060 Ti GPU with PyTorch library and Ultralytics framework. This diagram shows our full workflow from dataset to final results. Now let's look at the results. Both models trained smoothly over 100 epochs. YOLOv11M had a very smooth and stable loss curve. RT-DETR had more ups and downs because the self-attention mechanism is more complex and needs more computations. Let's look closer at YOLOv11M baseline results. Looking at per class recall, it performed based on patches, correctly detecting about 91% of true positive. Its weakest class are carrying at around 54% and roll-in scale at about 55%. These are the two hardest defect types for the model. Despite these weak spots, YOLOv11m only produced 329 false positive overall, showing it's still quite robust to normal steel texture. Now let's look at RT-DETR. Its per class recall is actually strong across the board. Pitted surface reach 92%, and its weakest class is the same with YOLOv11, which is crazing, but at about 75%, which is much better than YOLOv11m, 54% on the same defect. So RT-DETR is generally better at catching this hard low contrast defect. The trade-off is false alarm. It produced 1,519 false positive, far more than YOLOv11m, or at only 329, meaning it's often mistake normal steel texture for a real defect. After augmentation, YOLOv11m improved on most defect types. Crazing recall rose from about 54% to 61%, and roll-in scale from 55% to 60%. Two classes, patches and scratches, dipped slightly, but overall more true defects were detected, with true positive rising from 633 to 649. For RT-DETR, it's quite different. Augmentation cut false positive by 64%, from 1,500 down to 545, which is a very big improvement. But recall actually dropped on almost every single class, not just one. For example, pitted surface fell from 92% to 84%, and roll-in scale from 78% to 65%. This tells us RT-DETR's global attention mechanism is more broadly disrupted by spatial augmentations, not just weak on one specific defect type. This table summarizes all our results. YOLOv11m with augmentation gave the best overall performance with MAP 850 of 0.726 and F1 score of 0.711. You can also see that MAP 1595 is lower for all models, around 0.35. This is because steel defects have irregular shapes, making it hard to satisfy strict boundary matching. CNN-based models like YOLOv11m benefit strongly from aggressive augmentation and handle industrial variation well. Transformer-based models like RT-DETR give good recall but are most sensitive to background texture and to augmentation. This shows there are a real trade-off between the two architectures. To conclude, YOLOv11 gave the best overall performance and showed better robustness with augmentation. RT-DETR greatly reduced false positive but with a small recall trade-off. For future work, we plan to explore hybrid CNN transformer models and design augmentation strategies that are tailored specifically for each architecture. Thank you for your attention. I appreciate your time, and I welcome any questions or feedback you may have.